let's talk about motor control and drive. What kind of power solution would you choose if you were working on a motor control design? Gallium nitride? Yeah, I would too. But what if that motor control design was specifically for a power tool? What then? What would you expect to be the biggest benefit that this kind of power solution would bring to the table in this case? Well, my friends, that's exactly what we're talking about today. Hi, I'm Amelia Dalton, host of Chalk Talk. In this episode of Chalk Talk, Art Gonsky from Nexperia and I discuss the biggest challenges of electric motors and controllers, and how GaN power solutions can help solve these issues. We also investigate how silicon carbide, and GaN power solutions compare, and how Nexperia and NXP technologies can get your next motor control design up and running in no time. And before we get started, don't forget to click that link. There you can find even more information about this topic from Nexperia. Hi, Art. Thank you so much for joining me.
Thank you, Amelia, and it's my pleasure to join Chalk Talk with you.
I'm happy to have you. So, Art, we're talking all about GaN power solutions for motor control and drive today. But before we look at the solutions in this arena, walk me through the evolution of motor control and how the design requirements have changed over the years.
The motor control evolutions started around the 19th century, and that's with Tesla, believe it or not, because he was the inventor of the first electric motor and he patented as well. And basic DC motor after that, it was essentially a commutator with brushes to control the speed. A lot of sparks came through it, was extremely noisy, but it was spinning and it was actually driving loads. So it was a very inventful approach. The control of it was extremely limited to the on-off switching and a very simple voltage resistance-based speed control. And it also had a what used to be called a governor, that if the motor ran away or the speed was too high, it would just clamp on the shaft and it would stop the motor in a very barbaric kind of a way. But the key milestone is the Faraday worked electromagnetism enabled development, and the Davenport had the first working motor in 1834. So that was a pretty good start from my perspective. And 1905, they actually had the first production motor delivered that worked just about everywhere. In the analog era, mid-20th century, I remember like it was yesterday, the transistor invention, thank God to some of the scientists in the US, enabled higher frequency and more efficient switching. And pulse width modulation, called PWM, also allowed precise control of speed and torque. And so that gave us another leg up on how that motor is controlled, and we can vary speed and we can vary torque for different loads and different applications. The analog servo amp, which improved accuracy with the feedback control. And if you can picture the motor, if you spinning the motor, but it has to stop at a precise point, or maybe execute 3 or 4 turns and stop at a different point at, let's say, 120 degrees or 129 degrees. That's why the analog servo amplifier actually improved accuracy and created the first feedback control of the device on the motor. The variable frequency drives enable variable speed control of the AC motors via frequency adjustment. And that is very obvious now in some of the newer pool pumps or hot tub pumps or anything that requires a inexpensive AC motor that you can vary frequency and you can actually vary speed. And so that gives you a much better efficiency. So as the refrigerators without using a DC motor and a complicated and a little more expensive version of it. But the digital revolution, and this is late 20th, early 21st century, the MCU, the microcontrollers, and the DSP, digital signal processing devices, enabled real-time control and a very advanced algorithms. It also included sensorless control, FOC, and MRIS, which reduced reliance on the physical sensors. And it's the active feedback with a field-oriented control, and also digital torque control that is being progressed and in modern development right now. It gives you a very precise, better than a degree of accuracy of that motor shaft being turned. The BLDC motors, a brushless DC motor, essentially gained traction for efficiency and low maintenance because there's no more brushes. So there's nothing to wear out. And that gives you a pretty good idea where BLDC motors belong in the future, even though it is a little more expensive. But as we keep on going and the motors manufacturing becoming less expensive, and so is the control system becoming also less expensive, putting it together is a different story. But that's why we're here and we're working with the digital guys on the control systems, analog and digital. the smart and connected motors. So the IoT integration for monitoring and optimization. And if you can picture robotics, any robotics, assembly type, this is BLDC motor 100% because you can have a much better control, no wearing out, and you can actually control that from a remote position. You don't have to be there any longer to plug in. The current trends in the future outlook. So advanced motors, synchronous motors, which offer very high efficiency with less rare earth content, which is an expensive metal this day and age, but it still requests premium for such motors, even though there's a little of the rare earth type metal inside. Of course, the AI integration, everything is going to AI and predictability, which enhances control strategies and predictive capabilities. It also can predict the possible failure of the motor and the motor circuit that's involved with that. So the digital twins, which enable simulation, diagnostics, and proactive maintenance. And that is giving people that have never dealt with the motors, which is not an easy job, in my opinion, to work with. It gave them the access to tools that will make them nearly genius when it comes to the motor setup and motor operation, motor control, and the motor maintenance. That gives us a pretty good idea where we are now.
All right. So, Art, give us a refresher on motor control. Brush DC versus brushless DC. What are the benefits that each solution brings to the table?
Brushed DC is when you actually have two brushes. It applies positive and a negative voltage, and that spins the actual armature of the motor. The problem with that is you have brushes that are touching metal, and as it spins, the brushes actually create noise, create sparks, and has issues with interfering, let's say, with a cell phone if you're in a near vicinity. So that is not that easy to pass what we call an EMI, EMC, electromagnetic compliance testing. The good thing about brushed motors is they're extremely inexpensive and they're easy to control because all you need to do is to vary the voltage you're applying from, let's say, 0 full stop to, let's say, 12 volts or 48 volts, depending on what the motor is. But the main issue with that, the brushes will wear out, and that gives a increased maintenance intervals and also increased noise, also possibility of windings being shorted because there's too many sparks flying internally. So there's a lot of drawbacks to brushed motors, but there's some good things. There's always a silver lining somewhere. The brushless motors, it's usually a three-phase and the voltage applied in the sequential, let's say, pulse width modulation application approach. You switching from one control to the second control to the third control. Let's say if you have a three-phase type motor, which is very similar to the AC motor, three-phase that's running off the AC type application, with, of course, it'll run at the same frequency as the AC, 50 hertz or 60 hertz, depending on where you are in the US or in Europe. And the BLDC motor, you can control that with the pulse width modulation, and you can run that at a much, much higher speeds instead of just running it at 50 hertz or 60 hertz. 60 or 50 revolutions per second versus, let's say, you can do 1,000 revolutions per second with the BLDC, or you can do more than that, 10,000 revolutions per second, or you can do a lot faster than that, depending on the motor itself, the size and the controls. So for applications that require high speed and high torque, the BLDC motor is indispensable. And that has to work pretty much on from a zero torque application, so zero load, to the maximum load. If you can picture an example of a machine that picks up a roll of paper at the paper mill, it has to pick it up, has to move it somewhere, and then it has to place it on the shelf, second or third shelf, it doesn't really matter. And that can be 1,000 pounds. And so that gives you an idea where you have to be able to lift this, carefully move it without overshooting it, and place it where it belongs without losing the accuracy of it. And so this is where the BLDC motors are really good at. And they used to do a servo amplifiers, were good at that, and now it's a lot less expensive with a digital approach. The good example is the brushed DC motors were used extensively in the automobiles, fuel pumps. So if you can imagine a brushed motor with the brushes arcing inside the fuel pump where the fuel is combustible, it's a gasoline. And so most manufacturers have moved away from that and went into the brushless motors. And so that would last, I can't say forever, but certainly 10 to 20 years longer than the brush DC motor. So brushless, something is that safe, easy to control, and the cost of the controlling system is being reduced every year.
So, Art, what do you think are the biggest challenges specifically with electric motors and controllers these days?
The challenges is selecting the proper power amplifier to drive them and mating that with a proper MCU or the DSP controller, which is digital, and being able to control that motor I guess, at about every application that we can imagine. And there's multitude of applications where BLDC motors used, from something small, let's say in a drone type application, small drone obviously, versus something that lifts big, like I said, papers, or just about anywhere in the warehouse industry. Also somewhere in between where you have assembly type robots in the automotive or any other assembly world. And now we're seeing the BLDC motors in the humanoid robotics, which you see now exploding all over the place. And so it's extremely wide use. That's why the motors are not going away, no matter how many software engineers will try to tell you that. The switching power coupled with the good controller of the MCU is extremely important. We have to make it invisible for let's say, an engineering to connect motor, power amplifier, and an MCU, and seamlessly being able to adjust. And this is where the AI is coming forth on something like that. So now all you have to do is just connect the motor, get the program to spin the motor. The MCU will register at, of course, at different speeds, will register the imperfections. No motor is perfect because it is still wound with copper and there's still magnets internally. The motor gets spun up at a few different speeds, stops, spins. The MCU will register that and now will understand the limitations of the motor and will adjust itself accordingly. So this is where the AI comes from. We're trying to make it as transparent as possible for engineers to connect that. And so this is where the controller, power amplifier, and the motor will come as a single piece for every other engineer who will work with that.
How can advanced MCU-based control architectures help solve these issues?
The original AI approach, it started back in the early 2010s, where Intel attempted to use what I guess I call the ubiquitous controller for the motor drivers. That started a trend where the Intel didn't pick it up on it, because I actually presented that to the Intel Development Forum back in 2013, I think. So it was a little interesting because they didn't jump on it. But later on, specifically the Japanese, they realized the connection between the MCU, power amplifier to drive the motor, and the motor. And the power amplifiers actually has to be changed depending on the size of the motor and depending on the need of the motor, what it can drive, and try to make it seamless and transparent. This is where the connection comes in between an MCU. MCU doesn't really care what size of the motor it's driving, but the amplifier does. And that MCU has to adjust to the combination of the amplifier and the motor connection. That will also provide feedback for the MCU in order to adjust how that motor is being driven and under what conditions and under what loads. And so the important part, MCU can be invisible in a way when it comes to driving a power amplifier for the motor, but it will adjust depending on what the need is. And so that gives you an idea where MCU will definitely become ubiquitous when it comes to driving a power amplifier, depending on actually, it doesn't care about the power that power amplifier has to produce. It can go from, let's say, a quarter watt or a quarter horsepower to maybe 5,000 watts to about 5 or 6 horsepower, which is quite a lot for the motor. That together makes a very compelling story where we can have the MCU, the power amplifier, or the motor driver in this case, and the motor as a single package. And the MCU will not care what that motor is as long as it can spin it up, it can check out the minimum, maximum, it can break the motor and then see what happens at that point, and it can adjust the firmware and, of course, the software. And then they'll have access to a person that will be working as a maintenance or working as a person that will use the amplifier to drive different type of motors to set it up. So it's a lot of different variations on it.
Let's also talk about motor control tuning. So how can we best match the MCU controller with a power inverter?
To match MCU to the power inverter or the power amplifier, it shouldn't be a trick. So the MCU doesn't care. You can use the same MCU, let's say 16-bit or 32-bit MCU, to develop an output that will drive the driver itself. But it will also depend on how that driver or how that inverter is driving that motor and how that feedback from the motor itself is being fed to the MCU. But there's also feedback that's being fed into the power amplifier in case there's something happens and the motor, let's say, shorts a winding, or you have a locked rotor, for example, so that amplifier or the power inverter will shut the motor down very quickly. But also that setup will be fed into the MCU so we can sense the speed, we can sense the torque, and we can look at the overall performance of the motor. And so MCU becomes, again, invisible and accessible, let's say, with a remote laptop or even with the smartphone. in order to change speed, to change torque, and to change how that motor is being controlled. This is what we are trying to achieve. The power inverter will change in size because of the motor it's driving, depending on what the motor power level requirement is, but the MCU should stay the same. The only change within the MCU will be the software and the firmware for that particular controller.
Why should we use GaN solutions? What kind of benefits does GaN bring to the table specifically for power tools?
With advanced motor control algorithms that have been around for actually a couple of decades now, the high efficiency motor control algorithm present essentially sense the power amplifier and what it has to do with the motor, and they will adjust accordingly. So it's a real-time adjustment for what that motor has to perform depending on the application. So direct torque control is something that it's much easier to use than the field-oriented control, which is FOC, and it's gaining popularity even though direct torque control is older than an FOC, but that gives you an idea for the high-speed range and the high torque range capabilities. Also, MCU will have self-test libraries and safety documentation that's certified by UL, and also European companies that are like UL. So the CISPRs, for example, and IEC's 6730 Class B and the Class A, also functional safety to make sure that if something goes wrong, the motor will be shut down hard and has to be restarted by, let's say, a maintenance worker or remote maintenance worker if it's not there. Also, you can have a scalable roadmap. Earlier, I was talking about that, where you can actually have a same MCU drive a motor that's a quarter horsepower or even fraction horsepower all the way to, let's say, 3 to 4 to 5 horsepower motor and everything in between. And with the same MCU with a different map setup, it can actually test the motor, of course, with an amplifier, as it say, running up to speed, and you can drive that motor properly with one of the map devices that you have in memory of the MCU. And of course, with something like that, the longevity program, even the 8-bit MCUs are still around. And so never mind the 16-bit and the 32, that's going to be quite a lot, and it's cost effective over time. And so that gives you a good idea where you could actually use that device over a period of maybe 10, 15, maybe even 20 years with a predictable maintenance as well. And also robotics, reference designs for autonomous lawn mower, for example, but that can also be used just about anywhere else. If you can think of, let's say, the pool type, a pool cleaner, which is also autonomous. If you can use it there, you can use it everywhere else, including hand tools. So with the GaN and the amplifier that's GaN-based with the same MCU, you actually increase the system performance to cost ratio. You can reduce the cost. It can also reduce the maintenance cost over time, let's say over 10 to 15 years. Safety and reliability, the MCU knows exactly what's going on, so it can shut everything down very quickly if there is a problem. You can pick whether it's an auto restart or it requires a maintenance person to see if everything is okay, and then restart it again, physically speaking. The system size decrease and weight, faster time to market, and it's very important. From 2 years in the past, we now to maybe 9 months, and maybe down to 6 months, give it a couple of years, as the integration levels will become higher in the same package. And so that's an important part. And of course, to reduce acoustic noise and the power harmonics.
So, Art, I know from previous Chalk Talks that different power technologies can be used for different applications. Walk me through how silicon carbide, and GaN solutions line up.
The lineup is very interesting because the silicon still, I can say, remains mainstream technology because it's slowly being removed by the silicon carbide and specifically gallium nitride. The target is sort of low to medium and to medium high power, which is about 6.5 kilovolts, and of course the kilowatts up there. But what gives you a pretty good idea with the silicon carbide MOSFETs and the silicon carbide diodes, they actually only capable of working at 650 volts all the way up to 1700 volts, and I believe there's 3300 volt devices that are being pushed in the market. So nothing below that. So this is for the high power, high voltage, moderate to medium high switching frequencies. The gallium nitride FET targets voltages from 40 volts to 700 volts, so everything in between, and it's low to medium power at the highest switching frequency, which you can run GaN close to 1 megahertz, and that's quite a lot because everything else becomes much smaller. Motor actually can be smaller with the same torque capability. Supporting components, passive like inductors and capacitors, can be reduced greatly, and so that's definitely footprint reduction and also reduction in overall size of the system, and it increases efficiency. So it's less heat. You don't need to use the same amount of metal for heat sinking.
Art, when it comes to GaN in particular, what specific advantages are we talking about?
First of all, you have no body diode. in GaN. So it's a much faster reverse recovery. And what that does, it shortens the dead time. So you can turn off GaN much, much quicker. And you also have a lot less energy residing inside that GaN switch. So when you turn it off, the biggest question is how quickly all that energy can be removed to ground from the GaN FET itself. And that happens much, much quicker. So let's say 10x reduction in the GaN being turned off. It's tens of nanoseconds, where you would actually have nanoseconds for silicon carbide, and you'll have maybe microseconds for the silicon MOSFET. You can turn it on much faster, and you can turn it off even quicker than that. So that gives you a much smoother voltage waveform that goes to the motor, and the motor runs much smoother, and it also results in longevity of the motor. So it has less vibration overall, and that gives you a pretty good idea where, let's say, the bearings and everything else inside the motor, if it's vibrating less, it will last a lot longer than, let's say, with a silicon MOSFET at the lowest switching frequency. You can see it in the pictures that there's a shorter dead time that will make voltage and the current smoother, less choppy, so much smoother operation. That means lower distortion, fewer vibrations, and a quieter motor sounds. A good example is there's a company called Da Vinci, just one of few out there. They do surgical robotics. And you can imagine, you actually looking at the nano, if not pico meters, in order for you to get the surgery done. It has to be extremely precise, and that has to depend on the motor's smoothness, where you start, where you end, and where you lift that scalpel from the robotic system. And so GaN has the biggest advantage in the applications like that. Of course, in any other controlling type applications of the motor. Smoother torque gives you a lot more efficient motor, and all power tunes into useful work, so no wasted energy. And you can get close to, let's say, 90% efficiency versus 70% efficiency or maybe 60% efficiency with the silicon MOSFET. The dead time elimination also gives you the same idea with the actual dead time insertion will be 6 torque discontinuations per electrical cycle. And that is being smoothed out by GaN as well. So by reducing torque ripple, the motor is smaller, quieter, and cooler. Your passive components reduced size-wise. Audible noise is also reduced to the point of we not be able to hear it. Maybe some dogs will. Much better thermal handling, so the heatsink can be much smaller if you even need a heatsink, depending on the power level. The higher control precision, like I mentioned, robotic surgery, for example, and a much cleaner EMI profile, so you can pass the EMI EMC, and you can pass even the CISPR 22, which is the most difficult EMI EMC that Europeans have put on us, engineers. And so that gives you a good approach to rethink how the motor drives operate and look towards the new technology for something like that. So I think that's very important.
When it comes to this most recent generation of power tools, what specific motor control design requirements are we looking at? And how can NXP and Nexperia help solve these issues?
NXP and Nexperia, by working together, we bring experts from the MCU, MPU, and the DSP group that NXP has and had it for quite a while, with our motor drive specialists that have been doing power or power inverters, not just for the motor application, for just about everything else that requires, let's say, a 3-phase type power operation. So we have experts on our side, and NXP has expert on their side, but putting things together, this is where we shine, because we can actually go back and forth in real time and have a better understanding how the MCU will operate in conjunction with the power inverter and what motor is being used. How can we reduce, let's say, the tuning time, the tuning cost, and how can we improve the combination of the MCU, power inverter, and the motor? What that also gives us is the new motor, and the motors are usually not very easy to change. And so with the new MCUs and the new inverters, GaN-based, for example, in this case, the realization that you not require, let's say, the motor of the half horsepower to drive what a quarter horsepower motor can do now, because it's much smoother, much more efficient. And so that gives the idea that the motor manufacturing guys, motor engineers, it's not an easy job to design a new motor and to create, manufacture a new motor, but they're always like behind the actual electronics, because motor is basically mechanical. Everything is mechanical in the motor itself. And that becomes one of the main issues why the motor's kind of always like behind this. But now, with the combination of the MCU and a power inverter, the motor itself can change. And we will accept that because we can see where the motor can be in, let's say, 10 to 15 to 20 years versus where the motor is now. And they can change the material inside the motor. They can use better bearings, let's say go from the stainless steel balls to ceramic bearings, for example, to get the higher speed for the motor. And so that actually puts not a pressure, but on the final system engineers, they will be asking, how can we get a better motor to go with the better power inverter and the better MCU? So to me, I think it's not just one step, it's a few steps in the right direction to have a system approach solution.
So when it comes to overvoltage, how does GaN compare with silicon FETs?
GaN itself, due to the internal structure, is actually capable of overvoltaging itself by about between 20 to 30%. So if the GaN, let's say, rated at 100 volts and it's spinning a 96-volt motor, which if you, for example, take a look at some of the Ryobis and DeWalt's battery-operated lawnmowers, you can put two 48-volt batteries and they get you that 96-volt operation. By using 100-volt with a silicon MOSFET, it's unthinkable because you're going to overvoltage that very, very quickly. With the GaN, you can actually do that up to 120 to maybe 130 volts. The question is how repeatable. So some manufacturers actually state that in their data sheet. Nexperia, we're a little more cautious with something like that. What we do, we actually recommend protection on the output, that if you do, let's say, overvoltage the part, we have a clamp on the output that it will not permit to go, let's say, above 110 volts, for example, or 100 volts even. And so that gives you an idea that our part can survive a lot longer in the application than, let's say, somebody without the knowledge. The point about GaN, it's a fairly new application in the motor control business right now. And we're trying to educate customers on why the GaN is better, why this, in certain applications, you have to use, let's say, brakes, like in the motor vehicle, you have brakes. And so you need that, especially in some of the newer cars, you have automatic brake system. If it detects something up front and you, on your phone, it'll stop the car. Same thing. We're trying to make customers understand, have them educated on how we can use GaN. Yes, it can be over voltage a certain amount of times. Still, something like that, you need to be able to put a brake on it if need be. And so this is where we are with GaN. But it's capable of going over voltage by about 20, 30%.
I know that Nexperia has a robust portfolio of GaN solutions. So what do you think are the biggest benefits of Nexperia GaN solutions for designers today?
The reason Nexperia is ahead of competition, even though, let's say, our portfolio not as wide and as deep as some of the much bigger companies than Nexperia, we have experts from every aspect of the switching power technologies, and we also have experts in what the internal structures are for the gallium nitride and the silicon carbide, and how that compares to, let's say, silicon MOSFET. We also have application people that have done quite a lot of different applications, and that's the motor base, the audio amplification base, and just about anything else. That would be GaN, silicon carbide, and it will be based against the silicon MOSFET. For example, I have 40 plus years, 2 different countries for the switching power, and I came from linear. I came from the military world, the radar systems. And so we have experts that have done the motor drivers like myself. We've done some of the, let's say, magnetic resonance imaging amplifiers with the switching power that's going to move into GaN. So not just motors, and also CT type scanners you see in the medicine, as well as in an airports. If you've been in the airport lately, there's sort of a long white tube, kind of a high in the middle, a little less on the inside, on the outsides. But a switching power is here to stay, and we have collected experts not just on the physics of the devices, silicon carbide and GaN, but also how our experts describe where the GaN and silicon carbide can be used, and specifically in, let's say, motor drivers, audio amplifiers, and anything else that requires switching power to be present, so power inverters. And I have to mention the photovoltaic and the battery backup systems. You have to have a power inverter for the DC to convert to AC. Again, it's the same topology, and believe it or not, we should be able to use the same MCU that can control that, but of course, in a different mapping world. So we are in the onboard chargers for the electric vehicles, and that's also going GaN because it reduces size, reduces weight, and everything is sort of moving towards switching power, whether it's a single phase or whether it's a 3-phase. It's giving us a pretty good idea of where we are now. That's why Nexperia always has experts in every field that come together and work with our system and also combine it with the NXP MCUs and put everything together for the seamless system transition. The Cascode is a very advanced approach to how the GaN is being packaged. The key to the Cascode FETs and our package at this point is a what we call a CC pack. And the main reason for the CC pack being what that is and why I like that. Internally, there's nothing but clips, or as we, the older generation, call it bus bars. Most of the packages, internal packages, even for the newer GaN applications from the bigger companies, I'm not naming names, have what we call bonded wires. And every time you have bonded wires and you're switching high power at the high frequency, that becomes a very high inductance that generates a lot of losses, a lot of noise, and also extra heat that is not needed. With the CC pack and the cascode/D mode, that is completely removed. So there's not a single bond wire in there. And therefore, you can switch this at a much higher frequency and at a higher power level. And if we can compare, let's say, a lower resistance devices from our competition, but using the bonded wires internally in their package, our part at the higher power, that's where they all operate anyways, actually is a lot more efficient and has a lot less thermal dissipation than the competition does. So we do not waste power. We're trying to confirm that.
Walk me through the cascode GaN FETs.
The key for the D mode/cascode is there's actually a 2-die operation. One die is the HEMT, high emission electron mobility, but it also has an extra 30-volt silicon MOSFET that is creating a gate driver internally. So that GaN looks just like a silicon MOSFET, which most engineers know exactly how that can be driven. And it accepts higher voltages, let's say from 4 volts all the way up to 10 or 12 volts, and it can withstand plus or minus 20 volts. And so it's a little more complex, a little more expensive to manufacture, although we have pretty much removed most of the cost from it, so the customer doesn't see it as much, and it's a much higher power approach.
Okay, so what about E-mode MFP GaN FETs you mentioned earlier?
The E-mode is what GaN FETs originally were created as such. It's an extremely sensitive gate where the D-mode GaN has no problem with the gates being driven like a silicon MOSFET, I said, where with the regular E-mode GaN technology, you have to be very cautious of how the gate is driven. So that part can be turned on at 1.5 volts versus 4 volts for the D mode. Same thing goes for the turn-off. And that gives the idea of the drivers that the gate is so sensitive, the layout has to be extremely sensitive as well. Everything has to be placed just so, not much room for a mistake. A lot of noise can enter the gate because it's not noise protected for the E mode, but you can drive it at the much higher frequencies, but at the lower power. So there is a approach where the D mode or the cascode GaN is used for the high voltage, 650 volts, higher power applications. You can drive that part 80 plus amps. And with an E mode, you can only drive that part maybe 30 amps or less. And that's even at the same voltage. That's at the 650 volts. The E mode comes to shine at lower voltages. At the 12 volts, 40 volts, for example, 100 volts, and 150 volts. You can definitely use E mode because we know the power levels going to be much lower than at 650 volts and the voltage.
So, Art, what does the overall Nexperia ecosystem look like here?
The ecosystem of Nexperia is going from 40 volts, which is bidirectional GaN in the chip scale or the QFN package, all the way up to 650 volts in a cascode in the CC pack, which is probably my favorite package as of late, and the TO247, which has been around forever. Not as long as I have, but definitely not far from it. The beauty of 40 volt bidirectional, that anything that's the battery operated, that is a perfect part for it because it's bidirectional. So in order to protect battery protection, or let's say turning the battery on and off, right now, 2 parts are being used. 2 silicon MOSFETs back to back. So that gives a much higher resistance and not that great to control. The 40 volt bidirectional part can be used just one, and it gives much, much lower RDS on, down to 1.2 milliohm. And so it's an easy part. I'm going to see this part probably in 99.9% of all the low voltage battery applications. So the E mode GaN, the 100 volts and the 150 volts and even 650, 700 volts also has its places. The 100 volts at the 48 volt battery application, even though this is not bidirectional yet, but we're working on it. The power supply is AC/DC for the fast charging in the e-mobility world. That gives you USB fast charging. Also, if you have a USB-C type device, and if you look on, let's say, Amazon, if you look for the USB-C, you will see a lot of chargers, plug-in chargers, that says GaN inside. And so now you know that switching it to much higher frequency, it's a very small charger itself, let's say half the size of what it used to be for 65 watt output. And that's what requirement is. And that's, let's say, that's how I drive my laptop that requires 65 watts. And I have the charger that size of a lipstick, for example, except on the square side. And so that gives you a pretty good idea. 150 volts, that's a Class D amplifier audio. The companies are moving up in voltage. And so we're also working with them on something like that. And that's towards 650 volts for our DFN package, let's say at 80 milliohms. And so the higher the bus, the easy it is to drive, and you can still drive it at the higher frequency. That's a pretty good idea of where the GaN is proliferating. And you can drive our 650-volt GaN and soon 700-volt GaN at up to 1 kilowatt. And so datacom, telecom, microinverters, you basically build DC motors again, chargers, LED drivers, and the GaN is really proliferating itself into just about every industry in the cases like that. It makes it easier to work and easier to understand where we are. The Cascode GaN, that can work up to 10 kilowatts and higher application because of the internal structure. Call it bus bar. So any onboard chargers. So if you're charging the 400-volt battery on an electric vehicle, the GaN is really being looked at by the automotive companies because, and this comes from one of the VPs from the Audi from a few years ago, every pound you save from a vehicle saves you $20 in the manufacturing of it, which is very interesting. I wasn't aware of it. And so to me, it was an eye-opening experience. Traction inverters, of course, for the 400-volt batteries. Again, DC-DC converters, the solar inverters, and the UPSs, uninterruptible power supplies. And so we cover just about every application with our portfolio.
Can we also look at some specific applications as well?
Of course. So the typical application, I'm not going to go into the power supply of type, the USB type C charging type application, but in the motor control that you can look at the actual motor itself, whether it's AC large motor or BLDC large motor, you need your power converter. And this is where the GaN plays the biggest role as far as you getting that power that coming into the motor that needed, that will drive the mechanical load, whether it's a robotic arm or whether it's the forklift or just about anything else. But you also need the controller. And like I mentioned earlier, that control becomes not necessarily invisible, but easier to work with because it will have quite a few variations mapped internally. So you can pick one approach and you can see if the motor operates at that particular approach. If it doesn't, you change it and see if it works. Or there's some MCUs now that have a self-tuning, the software and the firmware built in, and they can actually drive the motor, see what the result is, correct itself for it, and then execute again, and then it drives through. So you also need, with something like that, you need compact design. And the main reason for that is right now, the MCU and the power converter are separate. So there's wires required to go from that package, let's say, to the motor. And now, if we can reduce the size, the MCU and the power converter can go right on the back of the motor, sort of plug in directly, and that will not lose any more power. It will be a higher efficiency. There's no need for high gauge wires, and it's going to be one unit, just the motor itself. All you have to do, just plug it in and connect motor to your load or shaft to your load, and that will work through it. So efficiency and reliability, the smaller the components are, and you're also using less of them, the mean time between failures, MTBF, will be increased because you have a lot less devices that will fail over a period of time. So that's always a good thing from the mechanical engineering perspective. We never forget those guys. We work with them hand in hand. And so if they need that motor to operate 10 years without having anything broken, most of the time it will be electronics that will fail. But with the GaN approach, the higher frequency, size reduction, component reduction, that gives it a much better feeling for the mechanical guys that actually have to control the shaft going to the load. By increasing efficiency, reducing components internally, the devices run cooler. We can reduce the size of the heatsink. And also, we can remove the heatsinks depending on the motor size, of course. And so that gives you also a better idea. Even in the same motor size where you use, let's say, a 1 pound of aluminum heatsink, with our approach with GaN and the higher frequency switching, you can reduce that by 50% easily and use a half a pound worth of metal instead of 1 pound. And so aluminum is still expensive, and that gives you a pretty good idea where the savings will come in with the thermal management. Bipolar power flow, if we're using bipolar devices, depending on how much power you need to flow back, let's say, to save, if there's a battery operated and you can charge the battery at the same time, that is about a couple of years away, but we are seeing it. And so the bidirectional devices at high voltage are coming. It will be another game changer from GaN because with GaN, it's much easier to have a bidirectional part than with the silicon carbide or with the silicon MOSFET. And so it's a win-win for everybody.
So why should we use GaN for motor control?
The very specific reasons, and I think the slide explains it really well, very low specific on resistance. So what we call RDS on, much lower gate charge, which are a lot more linear capacitance on the actual part, on the output capacitance, COSS, lower gate charge as well, virtually no QRR, which is the recovery because there is no body diode internally, which is parasitic to the silicon carbide and silicon MOSFET, even though people that get that, they know it's there, but they get it for free when I'm charging it for them. Here, it is removed. So the whole inductance in the package itself, specifically for the CC pack, where you have bus bars and not a single bond wire, that actually make it a very low inductance, so you can run it at the higher power and at the higher frequency with a better efficiency. And combined with, let's say, the field-oriented control or direct torque control, it makes it much easier to integrate the complete system in it. The benefits of GaN, essentially lower switching losses, and you can reduce the size of devices, much higher switching frequency, so the footprint becomes smaller because you're reducing the size of inductors and capacitance at higher frequency. The cleaner switching waveforms, so the motor is a lot less jittery. It's much smoother, like with the linear. So we actually going back, if you think about that, from the linear amplifiers, we went to switching amplifiers, and now we making our switching amplifiers look like the linear amplifiers, which is a win-win for everyone, especially me, because I do a lot of audio, kind of a hobby at home. So that gives you a pretty good idea where we are. And much cleaner switching waveforms. And so that means the EMI, EMC, easier to pass. And you cannot possibly put anything on the market these days without having that certifications from UL. Sure, at that times, which means you can switch it off much, much quicker. So smaller power stage, smaller bulk capacitor, which is still expensive. It's in the dollars range. Smaller heatsink, metal, still expensive. And possibility to integrate driver and the motor. Everything goes on the motor itself. And so, of course, it'll require a circular PC board and a case that will plug right into the motor itself. So that makes it very compelling to use GaN for this particular application. Torque ripple is also reduced, and so much more accurate motor, like I mentioned before, for the surgical robotics, for example, or just about any robotics that require precision. And going above 20 kilohertz, and in this case, well above 20 kilohertz for something like that. So much shorter at that time, so noise is reduced, and the total harmonic distortion is much, much lower, just like an audio amplifier requirement.
So, Art, one great application for this kind of power technology are hand drills. So how did we get to where we are today with this kind of design?
Originally, the bow drills, some of people I know still using them. Then you actually have crank-based tools, which I have one in my toolbox because I don't need to jump for something that's electric. And of course, Black & Decker, the pistol grip trigger switch model, which was AC motor, on-off. You can sort of vary the speed. I remember the very first drills came out back in the 70s. Actually, some of my neighbors used them back when. But portable battery power tool designs by Black & Decker and Milwaukee at the same time. Very durable and very powerful for professionals. So Bosch also has that. And of course, NASA has it. But now with the hand drills, the battery operating time, they would like to double it. So instead of, let's say, using your tool and have 2 or 3 batteries on hand being charged, in a charger, you can get away with just maybe 1 battery or 2 batteries. Instead of using it for, let's say, 25 or 30 minutes, you can use it for an hour. And that's where the GaN will shine, come through to something like that. Also, it will give a much higher torque, even at the same given motor, and much easier to control speed-wise. And you can get away with maybe 16-bit MCU, and it will look the same to whoever's designing the actual software in an MCU to drive a particular motor. So you can go from a regular drill to the impact drill to the nail gun to the shear handheld. So there's quite a variety. And we work with Stanley Black & Decker, Ryobis of the world, and the Milwaukee's, and my counterparts work with Bosch in Europe. And of course, there's quite a few companies in Asia that starting to utilize GaN for that. Also, the GaN is being used not just in the drill itself, but also for charging. And that gives the much faster charging for the actual, if you have a spare battery, and also cleaner and less size internally, even though the battery stays the same size. And that's a progress for everyone, not just the drill itself, but also for how the battery is being charged.
Okay, so Art, what about torque ripple? How do silicon FETs and GaN FETs compare in this case?
Silicon FETs, you see the 6, not just 6, but the 6 harmonic torque ripple at 160 kilohertz. That is very present, even if you feel it, let's say with the hand drill, and it's using silicon MOSFETs. You can still feel the vibration, even if you're just spinning the drill without applying load to that. So when you're driving a screw somewhere, you can feel it, that vibration much, because it gets amplified internally, and you can feel it through your hand. With the GaN FET, the ripple is eliminated completely. It's much smoother, more efficient rotation. And it's more useful torque instead of being wasted. And again, GaN is smaller, quieter, cooler. Passive components is smaller, audible noise is gone. And better thermal handling, high control precision, and you can operate your cell phone as you screws in your 2x4s, for example. You can use the phone at the same time and the headphones because it's much, much quieter. It has the EMI's signature profile, much, much lower. So there's virtually no interference with your electronic tools. And most of the, let's say, contractors, when they use their tools, there's usually a radio sitting right next to them. And with all the tools, you can actually hear that noise if you're listening to, let's say, AM, FM, or what have you. With the GaN, you do not hear that noise at all. And so that becomes something that's very interesting for a future exploration of the devices and how we can use them. It's more than just high speed. It's also high efficiency and high precision. You can't help it. The real-world data proves that the myth about GaN is wrong. Ideal for compact, battery-powered, or high-performance motor applications. And you see tiny tools right now being advertised on TVs. Let's say for the Father's Day, they're tiny, but they have an unbelievable amount of torque. And this is the GaN internally. And so you can actually have it with you. Also, if you have an air compressor that you have in your vehicle in case your tire goes flat or what have you, that's GaN. And now GaN moved into even smaller compressor that I actually carry with me on the bicycle. So I don't have to use a hand pump or a CO2 cartridge. And so that gives you a very good feeling when you have something like that. You have a sort of backup compressor that doesn't have much weight, and it's the size of a cigarette pack, if people remember what that size is. Most people don't probably, but that's a tiny, tiny size. Can pump your tire to 100 PSI, if not higher than that. So the GaN is really moving into the right direction.
So what about body diode reverse recovery? Can you explain that a bit and how GaN can also help here?
The reverse recovery, which is the issue with the body diode being non-existent at that particular GaN physics of the device. So when you're using a BLDC power inverter to drive motors, there's a high side and a low side. So it's 3 half bridges. So when the one MOSFET usually at the top turns on, the other one has to turn off, or vice versa. That becomes a problem because if the MOSFET, let's say, that has to be turned off is slower than the MOSFET that is being turned on, then we have a problem because all that energy will circulate and it becomes a lot less efficient overall. So if we can turn off MOSFET much quicker, so as the top part is being turned on, the lower MOSFET has to be turned off. And if the MOSFET is turning off much quicker, all that energy can go right through it without being wasted. And that is becoming one of the key points why GaN is so much better to drive motors or just about anything else for that matter. So the reverse recovery, which is extra power surge, it's how much current does the motor use and how fast the MOSFET will turn on and how quickly you can change speed. In many cases, we slow down the MOSFET to turn on because we have to compensate for the MOSFET that's slow being turned off. And right now, the problem is solved with the GaN because the dead time is going to be much, much quicker than with the silicon MOSFET or even with the silicon carbide MOSFET. And so that gives you a pretty good idea where it's very smooth and steady with the voltage change over time or the current change over time. So how fast you can turn on the FET, you can turn off the FET below, it's much faster. The benefit is a shorter dead time and the motor control faster and smoother and easier to control. With the shorter dead time, with the GaN FET, usually what happens in the inverter, it cuts the dead time, not just in half, it cuts it by a factor of 10, if not 50. So it's tens of the nanoseconds. So the results, the voltage is much smoother that goes to the motor, making it run better. And in many cases, it can also make it run faster. Because if the motor starts, let's say, vibrating because there's certain distortion at some of the frequency, at some of the speed. So let's say at the 100 RPM, it has no issues, but you go to 200 and becomes a problem because it has a distortion at that level. The GaN takes care of it. And now it's very smooth from the 100 RPM all the way to, let's say, 1000 RPM, revolutions per minute. And so that gives you a pretty good idea of what that does. The difference is, I explain it in the figure itself, as you can see, in each cycle, and this is going from negative to positive again. So one cycle, you have about 6 points that the motor vibrates on. And that also, these points could be increased or decreased depending on the RPM and depending on the torque requirement. And so the shorter dead time will make voltage and current a lot less choppy. And the harmonic distortion will be even across all the RPM ranges and all the torque ranges for something like that. So smoother torque, a better performance. We're removing those 6 bumps, which is actually more than that, but those are the worst of them all. And the GaN FET make torque smoother, a lot less wobble. So smoother torque equals more efficiency on the motor, and all power turns into useful work. There's no wasted energy. And so that makes it a lot easier for the people to operate.
Talk to me more about this dead time elimination. How can GaN specifically help me here?
So the dead time is the time between the top FET being turned on and the lower FET being turned off. And if there's a delay in the turn off, then that energy is getting wasted. But if the shorter dead time, it will actually become a smoother voltage waveform at the motor terminals because you can turn things off much, much quicker. All that will be reduced to ground with a much quicker you have a reproduction of a pure sinusoidal wave, which is needed, and total harmonic distortion, THD, is greatly reduced. And so that gives you a pretty flat response across, like I said, 100 RPM to 1,000 RPM or even higher, depending on the tool that is being used. The vibration acoustic noise is reduced. Like I said earlier, 6-stroke discontinuations per electrical cycle is also reduced. And those are the ones that we know about. There's actually 12 of them total. The other 6 are not as visible or not as felt as much as the first 6. And so applied torque is much smoother. The motor is a lot more efficient. And torque to current conversion is also a lot more efficient. So you can actually get higher torque with a given motor that would not be able to get that done with a silicon MOSFETs.
Let's step back a bit. Art, explain to me about why electric motors are more efficient at higher speeds.
Primarily, the way losses and power output scale with speed. The problem with the higher speed electric motor is that you actually get less torque out of it. But with GaN, we actually increased the torque range, even at the higher speed. And so the primary, and it depends on physical factors and electrical factors of the motor itself, because still, it's a mechanical device, and it has to operate in certain conditions because of the designers, like I mentioned earlier, the windings, the size of the wire, the magnets inside. And so at low speeds, the iron losses, which is the hysteresis and eddy currents and frictions, will dominate. But it gives you the highest torque. The motors are kind of funny this way. At the 0 RPM, you get the highest torque of the motor. And as the speed increases, the output power increases faster than the losses. And so higher roll efficiency, you will lose on the torque at the higher speeds. And a good example is the electric cars with a pure electric motor drive. At the higher speeds, the torque is reduced greatly with this particular type of the application. Improved cooling with speeds. There's internal fan, usually 2, one right by the shaft on the output and one where the actual wires go in. As the motor spins faster, the fans that's built into the shaft also spin faster, so that gives you better cooling. And it's the airflow going through. So higher speed, more airflow, better heat dissipation. The motor will stay near optimal temperature, so much better performance. The magnetic circuit, the way it's getting utilized in the motor, which is the faster field cycling, will improve the energy conversion, especially in the AC motors. We can still use GaN, and we do use GaN for AC motors, specifically the 120 volt ones AC and the 240 volts AC motors for your pool pumps, for just about any type of application, for your irrigation pumps, you name it. Also, with that, it gives you a higher torque to loss ratio. Also, lower relative copper losses, so I squared R, and it's the current squared based on the resistance. Again, internal wire, as you're winding, will give you a certain resistance on that device itself. And if you can get the power output to rise faster, then the losses become smaller. So if you reach that peak quicker, let's say instead of 1 second, it's a half a second, you're going to lose a lot less power, percentage-wise, something like that, because I squared R. You have no choice. As the current rises by the square, if you can reduce that by 50%, that gives you a much better performance. And you get efficiency gain at the higher output levels. The way we drive the motor, specifically the variable frequency drives that are being utilized now, even in the US, because we kind of run behind Asia and Europe with something like that, also will match motor frequency at the higher speed. And the motors are designed to operate at a certain speed envelope, if you will, between, let's say, 100 RPM and 200 RPM. And so at the lower speed, they get less efficient. At the higher speed, they also get less efficient, but right there in between, because the motors can have the same efficiency across the whole speed range, especially AC motors. And so when we work with the designers and find that design point that's optimal, that reduces electrical mismatch. And we work with a system, and an MCU actually takes care of it as well. It can be programmed to work and to find the optimal minimum maximum speed of that envelope of the motor. The high speed limitations, of course, of the windage and the bearing drag, and that's why they go into ceramic bearings now, which is kind of nice. The conductor skin effect and the eddy currents, and they go into a multi-stranded wire. Of course, the saturation and thermal limits. The motors are very mechanical. They're not moving up as quick as, let's say, the electronics and an MCU and the power inverters or the amplifiers, but still, where the motors are now compared to where the motors were, let's say, 20 years ago, it's night and day. And so we're moving in the right direction. So this was an experimental validation that I've done here. The 36 volts DC input, 5 amps current, which is nothing to sneeze at, and I run it between 20 and 100 kilohertz switching frequency. And so what happened when you look at the table, the output power, input power, torque, and efficiency. So with the silicon, we were running at about 79, let's say 80 watts. With the GaN, it was also 80 watts, but the input power was 121 watts. For the silicon, 113. So we reduced that by about 10 watts, the input power. so it ran a lot more efficient with GaN. The torque was higher at the same voltage levels, and the efficiency was up about 80 or so percent. And this was quick. And so it gave you the improved battery life, enhanced performance, quieter operation. Again, smaller and lighter tools in the end. Reliability is increased. And so the system and the life cycle has been improved overall.
All right. So, Art, before we go, walk me through the trends that you're seeing in power tools these days.
The key trends that's shaping the power tools, a bit slow to my liking. I like things to get a little bit faster, but intelligent safety. So the kickback detection, when you have a setting for a certain torque, when you, let's say, driving a screw into metal or what have you, when that torque snaps back, you feel it, not just your arm, but also your shoulder and the rest of the body. The kickback detection will actually control that in a cordless. And the government put a limit to that. As you can see, the IECs, the 63335 and 6730, and also 61508. And so that's what gives you a lot less strain on your arm. So you don't feel like your arm is going to fall off after you've done 8 hours of putting screws into something or bolting something or something in that category. So that is a very important step. And GaN controlled it really well. So greater power delivery, I explained it earlier. You have a much better torque with exactly the same requirements. So you have the battery technology improvements, much longer life. You can use a single battery for a lot longer than before. Noise ordinance regulations, so it's much quieter. I'm not sure how many people will complain, but there's quite a few that out there that would, neighbors, for example, when you're using that. And user preference for cordless, because the power lasts longer, you can drive it longer. You don't have to swap the batteries all the time, and the batteries are not that low priced. So that's a big deal. And also durability. EMI and EMC challenges, and that is if your, let's say, cell phone or your radio can operate near the tools that you're working with. Large voltage spikes are reduced also, and the important part, can operate at a much wider temperature range, minus 40 to 125 C. Let's say you're operating in Florida in August, and it's 95 degrees. You can see how the temperature rise that will give you, that tool will be failing at some point. Less heat lasts longer at the higher temperatures. And the security, the AP protection, the theft prevention, and tool tracking, and of course the battery authenticity. So you can't just buy battery, let's say off the Amazon and some unknown origin and plug it in. The device will not charge it and the device will not work with it. Also, I think it was DeWalt that went to a fingerprint. No one else can use your tool except people that programmed their fingerprint into the tool itself. And so that is also great security. Of course, an increase of the cost and a bit of complexity, but the safety is the biggest issue. And so that is part of the problem that we have solved with that.
Excellent. Well, Art, I think that's all I have time for today. Thank you so much for joining me.
Thank you very much, Amelia, for questions. And I hope we have covered a lot of good information on where the GaN is with the MCU and at the system level.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Nexperia. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EEJournal.